Good morning, everyone. Today we're going to cover topic 1.7 in our AP course, AP Calculus course. And this topic deals with selecting methods for limits. And on this first one, I think that we already have an idea of what we're going to do, don't we? Remember the conjugate? We're going to multiply the top and bottom by the square root of x plus the square root of 5 over the square root of x plus the square root of 5. It's kind of a giveaway. All right, anytime you see this kind of weird radical thing someplace, and of course, remember what step one always is. We try substitution. Okay, if I try substitution here, if I put the 5 in, I'm going to get a 0 in the denominator. I'm going to get problems. So we've got to do a plan B, which we learned last week, is some type of factoring or manipulation. So what happens after I get this? Well, the bottom is going to be a difference of two squares. So the bottom will turn into regular old x minus 5. Now the top we recognize as a difference of two squares. It factors into x minus 5 times x plus 5. But then we've got this other thing that we multiplied by, the square root of x plus the square root of 5. Don't forget that. And now we can start slashing some things. So I can slash those two things. And on some of these, just for the sake of time, I'm not going to finish evaluating them because at this point, I've got something that I can evaluate. I've got an expression that now I can plug this 5 in. There and there. And I can finish evaluating this limit. All right, because now I have it in a form where we can work. All right, so this is example 1. Let's go to example 2. And these are kind of, these sections I kind of like because it's just a chance for us to just crank out some good old-fashioned problems and learn some things. Now this is where I had told you to get out your trig identity sheet. And because if I try to substitute right here, what is the cosine of pi halves? Well, what I've told you to do is to come back and remember what the graph of cosine of pi halves looks like. Here's pi. Here's pi halves. The cosine of pi halves is 0. So right away, if I try to substitute here, I get a 0 in the denominator, which is a problem. All right. So that means we need to factor or manipulate. Factoring this thing doesn't do me much good. If I tried to make this 1 plus the sine of x times 1 minus the sine of x, that doesn't help anything go away in the bottom. So we don't want to do that. So when that won't work, we turn to a trig identity. And let's review a little bit. Sine squared plus cosine squared equals 1. That's a trig identity that we learned in pre-calculus. So I told you that if this is true, I could also write it like this. I could subtract sine squared, and I could say that cosine squared equals 1 minus sine squared. And that is actually the key to doing this problem. Because now that I know this truth statement, I told you last year that identities were truth statements. I can now replace this because of identities. I can now rewrite this as cosine squared x over cosine of x. And now it simplifies very nicely to just the cosine of x. And now I can evaluate my limit as x approaches pi halves. And I think we can see that's going to be 0. All right, so that was example 2. Now, this is example 3, and I don't know that we need to really go all the way through this one, but I want to get you started. When we did example 1, I can make that a little bit bigger. When we did example 1, I told you that anytime we see this square root of x plus or minus something, we need to be think conjugate. All right? Substituting is a problem. If I plug in my 1, I get a problem. So we need to manipulate it or factor it. Factoring it won't help us. So which conjugate should we work with? In this case, we want to work with the conjugate of the top. So I would multiply the top and bottom by the square root of x plus 1 over the square root of x plus 1. The conjugate is our friend. It really does help us a lot. And because on top now, look what I've got. I now have x minus 1 on top. This thing right here is a difference of 2 squares that becomes x minus 1 times x plus 1. I've still got this crazy little square root of x plus 1 over here, but that thing goes away. And I'm left with 1 over x plus 1 times the square root of x plus 1. And I can evaluate my limit now by substitution. All right, so yay for us. We did good there. Let's move on. Try to keep this thing in focus best I can. So here's example 4. And sometimes when it comes to using trig identities, if you look at your trig identities page, I think there is an identity statement for this top, but it really doesn't help us that much to substitute that. What works better is to remember that sine squared plus cosine squared equals 1. That means I can replace this 1 with this on this particular problem. Let's try it. Now I have 2 cosine squared theta minus, I'm putting it in parentheses on this first step, sine squared plus cosine squared. I replace the 1 with sine squared plus cosine squared. The bottom is cosine theta minus sine theta. Now on top, look what happens. I take this minus through, and I have 2 cosine squared theta minus sine squared theta minus cosine squared theta. All right. And now look what I have. I have 2 cosine squared, and over here I have a minus cosine squared, which means I only have 1 cosine squared. So now I have cosine squared theta minus sine squared theta over just cosine theta minus the sine of theta. And I still can't evaluate the limit quite yet. But do you see what the next simplification is? Do you see that this top is a difference of 2 squares? The top is now a difference of 2 squares that will become the cosine of theta plus sine theta times the cosine of theta minus sine theta all over cosine theta minus sine theta, and there's my slash point. And now it is a nice, friendly limit to evaluate. I may go ahead and finish this one for you since it has those scary trig things in it. How would I find the cosine of pi fourths? if I wanted to find the cosine of pi fourths without a calculator, we're assuming we can't use calculator on all of these. Well, I remember that this is 45 degrees, and I go back to our bow tie method, draw my triangle. If it's a 45, 45, this is 1, 1, radical 2. And so we remember that the cosine of 45 and the sine of 45 are the same thing because of these ones. They're both radical 2 over 2. All right? And so a half plus a half makes a whole. This is just the square root of 2. All right, going back and using the bow tie method. Piecewise function. We'll see these. So we're doing the limit as x approaches 6. The limit as x approaches 6, which means if I put in 6, I get a 0 in the denominator, which is a problem. This is a piecewise function, and what we should probably consider is this thing right here. Look what we've got. I've got the absolute value of x minus 6 over x minus 6. All right, times x plus 6. And so if you remember, what we want to do is we want to think what's happening with this thing as we approach from the right and the left. We know that on this graph, when x is 6, the value of this thing is 0. They told us that. All right, they gave us that little fact. I'm sorry, it should be over here at 6. 1, 2, 3, 4, 5, 6. It should be 0 over here, not there. All right. But what's happening as we approach from the left and the right here? If I were to pick 5, let's look at this numerically. The absolute value of 5 minus 6 over 5 minus 6 times 5 plus 6. Well, this is going to be 1. This is going to be negative 1. All right. So it looks to me like this is going to be negative 1/11. Right? And if I were to pick a number even closer, it's going to become an even smaller fraction. All right. Like let's say that I were to do 5.5. If I were to do 5.5 minus 6 over 5.5 minus 6, and this is 5.5 plus 6. This part here is still negative 1. We remember that from our other time we looked at that function, and I'm going to be left with negative 1 over 11.5. So the closer that I get to 6, all right, the smaller this thing becomes. Do you agree? Isn't this thing right here going towards 0? It is. All right, it's going towards 0. And if I were to look at it from the right, it would be the same thing. Now, what's happening as we go way to the left? Like if I were to look over at like negative 30 or something. At negative 30, I would have negative 30 minus 6, absolute value of negative 30 minus 6. And here I've got negative 30 plus 6. All right. This thing here is still going, it's going to wind up being a negative 1. And I'm going to have negative 1 over negative 36. All right. Which is still a really small number, but it's positive now. So it kind of looks like this thing was up here a little bit, kind of dipped below a little bit, and now it's approaching here. this limit, left and right, what would happen if we looked at it from the right? We would see the same thing. If I were to do from the right, the absolute value of 7 minus 6 over 7 minus 6 times 7 plus 6. All right, I'm going to have 1. This thing is going to be 1/13. All right, I'm going to have 1/13. And the closer I get, like if I were to do, what happens here? If I do, what if this would have been a 6.5 now? Well, now it's going to be 1/12. And this is why we need to consider what's going on here. This will be 1 over 12.5. It's not getting smaller, it's getting bigger, isn't it? Is this approaching 0 now? Doesn't appear to. Okay. As a matter of fact, what if I were to do 6.1? Well, now this thing is going to be 1 over 12.1. And the closer and closer I get, if I were to do, 6.01, now this is going to be 12.01. This thing is no longer approaching 0. All right. It's now looks to me like it's approaching 1/12. Okay. So this limit does not exist. And that way we had to kind of look at something a little bit different. Let me give you a couple of last minute tips here. This one, you know how to do this. This is factor by grouping. That's where you split it in half on top. That's where you do this. You pull out an x squared, you're left with an x plus 2, which means over here, I'm going to have an x plus 2, and I pull out a -1, okay, in case you forgot about that method of factoring. All right, and we're not going to have time to get to example 7, so we will stop there for today, and that does a very good job of covering topic 1.7. Thank you for joining us.